up until now, most of the reactions that we've studied are irreversible. That means it moves in one direction. We have reactants at one side, and once we increase the temperature or pressure or just mix them together, it will form a reaction and it will make products. All right? So it's one direction. But why are most reactions irreversible? Well, it's because it's usually when we have reactions out in the real world, in nature, and even in the lab, most of the time it's an open system. Okay, which means that the reactants here in pink are in the reaction vessel, and it's allowed to react, and when it forms products, some of it may be in the vessel, but if some of it happens to be gases or liquids, if the reactants are solids and the products are liquids, so the products may escape from the reaction vessel. In this example, I have drawn is where one of the products is a gas, and it will evaporate up. It will escape away out of the vessel. So you don't have products anymore, and so you only have limited products of another type of product that is left in the reaction vessel. So, but if the reaction takes place in a closed system, something here, you have, at the beginning, you have lots of reactants, and they are free to react. And when you form products, here, as drawn in orange, what you're going to see is that the products have nowhere to go. It's just going to be stuck in this vessel, in this closed system, and it's going to collide again with each other. And if the collision is energetic enough, in whereby it can overcome that minimum energy activation energy barrier, that minimum activation energy barrier, it can make reactants back again. So, in theory, most reactions are reversible if it's in a closed system. And so, how do chemists know if reactions are forward-moving or irreversible, or if they're reversible? Well, chemists use symbols. The one-directional right-pointing arrow yield as irreversible reactions. So in an open system, most of the time, you get like A plus B, and you get AB. This symbol here notes that it is one-directional and it's forward-moving. The arrow points to the right. But if chemists want to say that a reaction is reversible, no matter whether it's an open or closed systems, mostly it's closed system, then what's going to happen is that they're going to have right A plus B. These are the symbols to represent imaginary chemicals, all right? And you have this reversible symbol here to make AB. This symbol is comprised of two arrows, a half top arrow that points to the right and a bottom half arrow that points to the left. Now, this top half arrow that points to the right indicates that it is a forward-moving reaction. But the other arrow, the bottom half that points to the left, is a backward-moving arrow that points back to the reactants. So, think of regular, normal chemical reactions being as forward-moving. Think of it as me on a motorcycle. I'm using an analogy, right? Me on a motorcycle. And in a motorcycle, I am in an open space, right? The environment and me are right there. There's nothing, there's no cage covering or preventing me being exposed to the environment, okay? So, you know, if I'm on a motorcycle, most motorcycles, you turn the throttle or the accelerator, you move forward. It's really easy for me to go forward because all I do is turn the throttle and go here, go left, right? I I can go from KL to Penang and just go, right. But if I were to do a reverse on a motorcycle, it's very, very hard. I would have to put my foot down, I have to like move my foot in an awkward moving position where I have to like kind of walk backwards, and it takes a lot of energy. And so most of the time, chemical reactions are in an open, forward moving because it's in an open environment. But if it is a reversible reaction, like if you are driving a car, now that is different, right? Because most cars have a reverse gear. It's so easy because you are in the car. The car has a shell that covers you around, and you're in there, you're protected, you have nowhere to go inside that car. So you can drive the car forward by changing the gear to D, and then you can go backwards by changing your gear to R. So you can use that as a way to try to remember open and closed systems for reversible reactions. Now, here are a couple of, here are some examples that I've used to indicate reversible reactions. Yeah, there we go. Here we have ammonium chloride salt, right? If it's in a closed system, so you have ammonium chloride salt in the closed system, so it's here. And when you apply heat onto it, what's going to happen is that the molecules of the ammonium chloride is going to start jiggling, and it's going to break free because enough energy is inputted into the reactants. It's going to break free, and it's going to form ammonia gas and hydrogen chloride gas. So both of these are gases. So the gases are moving all around in the closed system. Now, if you take away the heat source, what is going to happen that the gases are start going to slow down, right? Also, when it's moving around, it's also going to hit each other. And what is going to happen is that gases, living products, right? What is happening is that the products are going to hit each other, and when they hit each other, the chemical reaction will occur, and it's going to form little particles of ammonium chloride all over the floor of the reaction vessel. So there you go. That's one example. Another example is where you have calcium carbonate, right? It's solid. And when you heat it up, it's going to become calcium oxide, which is lime, and CO2, which is flying all over in the closed system. Now, when you remove the heat, what's going to happen is that the molecules of the CO2 is going to hit the solid calcium oxide, and it's going to form back calcium carbonate. All right? So reactants gets formed. So when you apply heat, it goes to the right. When you let it cool down, it goes to the left. Oh yeah. The same thing for here. When you apply heat, it goes to the right. When you cool it down, it goes to the left. Right? Forward, backward. Reversible reactions. All right. Now, the final example is possibly the most important example you will encounter in this level of chemistry, which is the Haber process. We'll talk more about that in future lectures, video lectures. The Haber process is simply taking nitrogen gas and hydrogen gas. When you apply lots of pressure, when you close the system down, right? When you squish the system, okay? When you squish the system, what is going to happen is that you're going to form ammonia gas. And this ammonia gas is a very important precursor in the industry, because it's a precursor to make fertilizers and bombs. All right? But when you reopen the pressure system, what is going to happen, or apply heat, what is going to happen is that the ammonia gas is going to jiggle, break apart, and form the nitrogen and hydrogen gas back again. So that's it for reversible reactions, this introduction. we're going to talk about equilibrium and how to predict what happens when we manipulate this reversible equation system.